So, in order to have the three remaining lectures for cluster algebras, so I'm just going to dive into the cluster algebra formalism and machinery. So first, yeah. So let me tell you more or less what's the construction of a cluster algebra, how it goes. So one starts with a certain combinatorial datum, which is either a quiver, which is a finite directed graph, or more generally a skew-symmetrizable matrix, and a tuple of algebraically independent elements of some rational function field. And then using the combinatorial datum, one defines what it means to mutate the tuple of algebraically independent rational functions in with respect to any index. So let's say that there are n indices, let's say that the tuple is an n tuple, and then with the combinatorial datum, one chooses, one has the combinatorial datum, and then one chooses one index with respect to which one wants to mutate, and then one mutates the tuple by simply replacing the rational function at that index with a new one. And one also mutates the combinatorial datum, so that after mutation one can again do the same with respect to any index. So if one starts with an n tuple, one can mutate in n different directions, and then after mutation, one takes the result after any of those n mutations, and one can do the same in n different directions. And then again in n different directions, etc. And what happens is that in each step, one produces, you see, in each single mutation replaces one rational function. So one has almost exactly the same if one has two neighboring ones, but one has a new one, and then one mutates, and then what happens is that one starts introducing new rational functions. And then somehow when one considers the whole process, like after all possible sequences after all possible finite sequences of mutations, one obtains certain set of rational functions, and one calls those functions that one obtained throughout the whole process cluster variables. And then one considers the subring of the rational function field generated by the cluster variables, or sometimes it could be not the subring, but like the subfield or the C algebra if one is working on the rational function field with complex coefficients, etc. So depending on the context, one takes either the subring or the subfield or the C subalgebra, etc. But so the point is there is a notion of mutation that tells me, that is going to tell me in each step how I'm going to replace the combinatorial datum and this rational function that I replaced to obtain the new n tuple. Yeah? And that's how we're going to start with the matrix mutation. So here I have to say a couple of things. Yeah, so let's that this matrix mutation is defined. I haven't started. Sorry. So timer. So let's say, I don't know, maybe like this. Definition, and I know it's going to look a bit strange. So suppose that let's say b tilde is equal to, I'm going to write it like this, b and maybe I'm going to write c, that this is an integer matrix with n plus m rows and n columns. Right? So n and that it's skew-symmetrizable. Yeah, and by this, what I mean is that there exists an integer matrix, an integer diagonal matrix with positive diagonal entries. Yeah, and then the di's are positive, such that the top part, that it skew-symmetrizes the top part, so that this dB is skew-symmetric. So that this is what that this one transpose is equal to what, minus dB. Yeah. Okay, and then for each index k between 1 and n, the mutation mu k of b tilde is the matrix is the n plus m times n matrix, whose entries are given by, let's say, with a prime, let's say bij prime, let's say, is and it's divided into two cases. So it's minus bij if I is equal to k or j is equal to k. And otherwise, it is bij plus bik, absolute value of bkj, plus absolute value of bik times bkj, and this divided by 2. If so, in the other case, and this looks, this looks strange, I would say. No? I mean, this, yeah. Yeah, just don't tell Fomin that I say this. But.
So here the matrix multiplication with d is the other way around. It's n by n.
And with dB, with the top part. With the top part, yeah. So somehow I call the whole thing skew-symmetrizable if the top part is skew-symmetrizable. Yeah, and then the skew-symmetrizable, the notion is just completely analog to being symmetrizable, right? Like in the Cartan, for the Cartan matrices. Okay, so this admittedly looks strange. Let me say a couple of words. One is that, like the first one, what does it mean? It means that that, for example, if you look at the kth column of the new matrix, the kth column.
Okay, I have a stupid question.
Yeah.
I mean, I are positive. Okay, now I got it. So I was thinking about what's excusing the time of these. Nothing happened.
Yeah. Okay.
I'm back on track.
Okay. Now this I agree. It may look weird. At least it looked weird to me the first time I saw it. But here's the point is this: for k is one index from 1 to n. So k somehow represents a column. And this first what it's saying is that the new matrix, its kth column is just the kth column, the old kth column, but negated. So it's the new kth column is the old one because of the j here, but with all the negatives, including the whole thing, right? Including also the bottom part, and also the kth row, which is a row in the top part. The new kth row is minus the old kth row. So at least that's kind of easy to visualize. Yeah, and then all the rest of the entries look kind of weird, right? So it's kind of outside certain cross, the entries somehow may look weird. Now, I'm going to, instead of trying to make sense out of this, which is possible, what I'm going to do is I'm going to restrict my attention to the case where B is skew-symmetric, and I'm going to represent B by means of a quiver, and then state the corresponding translation of this mutation rule to the language of quivers, and in that language it's very easy this is very easy to visualize. So that's what I'm going to do. But I did want to mention this because it is somehow for the theory, it is important to know that there are cluster algebras in non-simply laced cases. So in cases that are not skew-symmetric, but strictly skew-symmetrized subtle, like in the case of like dinking diagrams, for example, that there are non-simply laced dinking diagrams which correspond to certain symmetrizable, and there are simply laced which correspond to symmetric Croton matrices. Okay. So if so, let's say definition. If B tilde is skew-symmetric, and by this I mean that the top is skew-symmetric, i.e. the B transpose is minus B. So in terms of the top, we define a quiver which is a finite oriented graph, Q of B, as follows, by setting the vertex set. The vertex set is going to be from 1 to n plus m. So n plus 1, etc., n plus m. And there's going to be, you know, and so let me think. Yeah. And for I and j here in Q0. The number of arrows from I to j. Sorry. Number of arrows from, not from I to j, but from j to I. Yeah. Is equal. I'm going to define it to be. It's Q-symmetric, so there's no problem. So it's going to be the maximum between Bij and 0. Right. I mean, here I'm. Yeah, this definition is slightly not very nice. So I mean, because you know, if so I and j. So if j is between n plus 1 and n plus m, I have problems, right? So that's what it's kind of breaking my head a little bit. So I mean, to be completely correct, I would have to say, you know, for I and j in yeah. So let me say, so I in Q0, and j in 1 to n. Right. Okay. And then now I don't have problems. Okay. Yeah. And then you see, in case both I and j are between 1 and n, then this becomes Bij minus Bji. I wrote Bij, sorry. Minus Bji.
Because Bij is minus Bj.
That's the number of unoriented arrows, maybe.
Okay.
Yeah, but we get always two times.
Yes, you are right. It's yeah. Let me leave it like this to not enter problems. Yeah. Okay. Anyway. Okay. And then this mutation becomes the following. Yeah. So given a but yeah, sorry. 1 second. Give me 1 second. I need to notice something. So notice that Q of B does not have loops. And by this I mean arrows that go from a vertex to itself, right? Not cycles, which that may perfectly be the case that Q of B has cycles, but loops. And it also does not have oriented two cycles. Yeah, okay. Yes, sorry. Yes. So this I shouldn't have gone into this other part. This was some wires crossed. But I think this is clear because in the diagonal we always only have zeros, right? And this other one also because we cannot have both Bij and Bji positive because if one is positive, the other one has to be negative. Okay. Now we say we call the vertices another definition. The vertices from 1 to n are called mutable. And those from n plus 1 to n plus m are called frozen. Some people call the frozen ones also coefficient vertices, but that's just okay. Now the mutation. Now the mutation of a quiver with frozen vertices. So let now Q be a quiver with 1 to n mutable. So 1 to n are mutable vertices, and n plus n plus 1 to n plus m frozen. And then for k, again in one of the mutable directions, the mutation mu k of q is given by following the next three steps that are going to be actually 4. So step 1, so it's like the Musketeers, no? That it's so in the first step, we look at every pair of arrows consisting of an arrow of Q coming into K and going out, and the other one going out from K. So for every pair, let's say that what I have is this of arrows. Introduce or add a composite arrow, a new arrow. But from J, let me draw it like this to I. So I think of this step as introducing composite arrows, going through the mutating vertex, through the mutating index. Step 2. reverse arrows incident to k. Incident to k. And step 3. Step 3. Notice that in step 1, if originally I had an arrow from I to j, then in the step 1 I created an oriented 2 cycle, which then I would like to erase because I would like it to correspond to a skew symmetric matrix, that is to a quiver without oriented 2 cycles. So in step 3, I erase 2 cycles, and then let's say I'm going to say 1 by 1. So delete the arrows in 2 cycles, oriented 2 cycles, 1 by 1. And I say 1 by 1 just in order not to do this. So suppose I have like this configuration. And then you tell me delete the 2 cycles, then someone can say, okay, erase everything. But no, I mean, what I want is just to erase this arrow, but with one of the 2. I don't want to, I want to pair it with one of the 2. I don't want to erase both of these at the same time. So that's it. Some other people say choose a maximal collection of disjoint 2 cycles and erase this maximal collection. So that's what several authors say. And then the 4th step, you see the point is that also in the first step, somehow I could have created, if both j and I were frozen, I could have created an arrow in the first step. But somehow, when I define the quiver q of b tilde, here there should have been a tilde, the quiver somehow doesn't see, the quiver doesn't have arrows between frozen ones because the matrix itself doesn't see those arrows. So step 4, which it personally bothers me, I always prefer not to do it, but in order not to create chaos once more, I'm going to say just delete arrows between frozen vertices. But in my opinion, the 4th step should not be performed, but between frozen vertices. Okay. And in any case, for the definition of cluster algebra, step 4 is irrelevant. Okay. So examples, yeah. So here you have, let's say, so one very simple example. So here I have this quiver. I don't have any frozen vertices. So here all the 3 vertices are mutable, and then I say mutate with respect to 2. So first step, look at incoming and outgoing, and for each such introduce composite arrow. So for this incoming and this outgoing, you have to introduce this composite arrow. Step 2, reverse arrows incident to the mutating vertex. So reverse these arrows. Okay. And third step, look for 2 cycles and delete them one by one. So here, fortunately, there's only 1, so delete it. So the result of mutating this with respect to 2 is this orientation of the linking diagram of type A3. Okay. Before going into the second example, notice, I mean, somehow what I want to stress is that notice what is clear is that in the end here the arrows incident to k in the end are actually the original arrows but reversed. And if you think about that corresponds precisely to this negation. That corresponds precisely to negating the entries incident to K. So when either K, where K is either I or J. And if you think a little bit about the other, you see this it is not hard to see that this corresponds to the creation of the composite arrows. Ignoring this corresponds to the creation of composite arrows. And the final addition, this one here of this one with this one, corresponds to deleting 2 cycles if there are any, or which happens when these have opposite signs, or if they have the same sign, it simply says the new composite arrows, consider them together with the old ones that were already parallel. So one can, with 5 minutes of thought, one can realize that. So I didn't work.
Does it work there? Yeah.
But then the fourth step is not taken into account by
The fourth step is taken into account by the fact that here you don't have columns here.
okay, yeah.
And
Of course.
yeah. Yeah, or if you want, now since you asked, it actually, the fourth step, what I don't like about it is that it corresponds to writing a 0 here in this bottom part. See, so yes, so that if you want, when you see, let's say that this one is skew-symmetric, then this matrix has a unique skew-symmetric extension by simply putting not unique, but you can put here minus C, whatever transpose, and a 0 here. Okay, this you can see, you can do, and then mutate using this. And when you mutate using that, there's not going to be a 0 necessarily on the bottom. But my step number 4 is saying, okay, put a 0 there. That's what I don't like about it. But okay, since I'm not considering this part, that actually is it's going to be irrelevant. Yeah, but there are more serious reasons why I don't like this. This is kind of when one seeks categorification, this step is, I don't find it natural. It's not natural to categorify, but whatever. Okay. And
so for step 2, you say reverse arrows incident to K.
Yes.
Okay, so not arrows starting from K.
No, incident. So both ending at K, the ones ending at K get reversed, and the ones starting at K get reversed as well. Yes.
Okay.
Yeah.
So, in the example I saw.
Right. Yeah. So incident, not starting or not only starting or only ending. Yeah. So everything ending at K gets reversed. Everything starting at K gets reversed. Yes. Yeah. And then another example. So here, which, I mean, you can see that it's an orientation of the Dynkin diagram of type A5. Not A5, D5. And then let's say mutate with respect to 3. Yeah? So it's for every pair consisting of an incoming and an outgoing, introduce a composite arrow. So since there is one incoming but 2 outgoing, it's for each of them, right? So here you have the composite arrows. next, reverse the arrows incident to the mutating vertex, which is 3, so reverse them. And well, and now there are not 2 cycles, so here is we already know that there are not 2 cycles. So here in step 3, in this case, do nothing. Yeah, because there are no 2 cycles. Okay. Notice, for example, that if the quiver, let's say that you have your quiver. Let's say one more example here. If your quiver has the property that the mutating vertex is a so-called sink, so that it doesn't have arrows starting at K, it only has arrows ending at K, and you mutate. Yeah, so here you have the rest of the quiver. So, and the mutation, well, the first step becomes void. Because you cannot form composite arrows. The second step becomes reversing, and you didn't create 2 cycles. So it's simply just reversing arrows incident at K. And same thing if you started with a source, that is if in your if now in your original quiver you had a vertex with the property that no arrow ends at K, the quiver only has arrows beginning at K, then it's again just arrow reversal for the arrows incident at K. Right? So here I can even say that this is, yeah. So, and you see, at least in this case, in these 2 cases, it's obvious that that mu k of the quiver is the original quiver, or let's say up to isomorphism of quivers, because you apply, it's just arrow reversal each step. But this is always the case, even in the less obvious situation where there may be composite arrows to introduce. So that's let's say a lemma. And this is easier to yeah, one can try to visualize it combinatorially at the level of quivers, and one can, and it's a kind of a useful exercise. But in the place where it becomes really obvious is for matrices. So mu k of mu k b tilde is b tilde, and this is really just taking this definition and then applying again mutation to this definition, and then just do the very basic algebra. Another property also is, and by the way, this is of course more general than just quivers, because this is for skew symmetrizable matrices. So this is for every b tilde in Z n plus m cross n skew symmetrizable. Another thing is that one question is, okay, but is mu k b tilde skew symmetrizable? And that's also the case, and this is also very easy to check that. So let me maybe rearrange this. So for every skew symmetrizable matrix, one has that b tilde skew symmetrizable, and with the same skew symmetrizer. So not b tilde, mu k b tilde is skew symmetrizable. I mean, here the problem with the symmetrizable and symmetric is that you cannot abbreviate them because they would have the same abbreviation. So let's say symmetrizable with the same skew symmetrizer and yeah. Okay, and these two things are a direct check, and what turns out to be a good kind of like a mental gymnastics is to try to visualize this for quivers, like that mutation of quivers is an involution. Yeah, of course I'm not saying. Of course, one can say mutate first with respect to one index, and then with respect to another index. But and that's different. That's not going to give me this. It has to be the same index. So, for instance, mu1 preceded by mu2 of b tilde. That is usually not b tilde. Okay. So that's mutation of skew symmetrizable matrices and mutation of quivers. Before keep going, so I have to say that these quivers with frozen vertices or skew symmetrizable matrices more generally are this the combinatorial datum that I said that is going to dictate me how to mutate the rational functions. So this is just the combinatorial side of this is the mutation of the 2B combinatorial datum for cluster algebras. And then you can still say, yeah, but it's still you still don't convince me. It still looks like a weird operation on quivers. So consider this. Another example. Yeah, and take yeah, let's say vertices 1, 2. No, but those are not the vertices of the quiver. Sorry, those are just the vertices of the polygon. Then I mean this is a triangulation of the square, and for the square I know I can draw either of them. Yeah. Now for each triangulation I'm going to define a quiver by setting the vertex set to be the set of diagonals in the triangulation. So the diagonals are the vertices, and I draw an arrow. Is it visible? Maybe not. Let me choose another color. Yeah. And then within each triangle, I draw an arrow. I draw arrows in the clockwise sense. So that's how the quiver of the triangulation would look like. So you have the triangulation T, let's say, T, and the quiver Q of T. It's another Q of T. Yeah, and then this I can do, of course, for any of the triangulations. So let's say that this is T prime, and Q of T prime. And well, here in this case, it is really easy to visualize that these two are related by a mutation. With respect to which one? With respect to the diagonal that is being flipped.
But so the vertices are the diagonal, and then you introduce other vertices based on where the arrows land.
No, I mean the vertices are the. So here I'm thinking that the triangulation of the square consists of this arc, this arc, this arc, this arc, and this arc. So it has 5 arcs. So the quiver has 5 vertices. And instead of drawing an extra dot, what I think is no. This is a vertex of the quiver, and this is a vertex of the quiver, and this is a vertex, and this is a vertex, and this is a vertex. Okay, and then how are the arrows? Okay, from this vertex to this vertex, there's this arrow. Yeah.
And, sorry, this is the natural way to define a quiver on a triangulation. It's like, in a very naive way, I would put the vertices in the vertices of the triangulation.
Right.
Which are the edges.
Right, that these would be the edges, right?
Yeah.
But something that I would find not completely natural is how to orient this, for example. In here, you can tell me, okay, yeah, come on, you can do the same, right? I mean, clockwise. Can you do that always? I guess on an oriented surface, you can always do that.
Or maybe you can
Yeah.
label the vertices and then orient like from the lower to the
Right.
greater.
Yeah. No, but let's say I'm already thinking. I'm already thinking if I can do this for an arbitrary triangulation of a surface with marked points. And then for such an arbitrary triangulation, you know, here in the case of the square, you can say, yeah, you can still make this an arrow from 1 to 2 by declaring that you orient it clockwise around that triangle. But if you go to the desired situation of a surface with marked points, there are some, let's say, loops for that somehow like for which you cannot say what is the clockwise and the counterclockwise, right? Because they don't cut off necessarily just a disk. They are not necessarily Jordan curves.
Okay.
So I would say, I mean, it's not that I just discard it. It's just that doing that from here to the desired case, I find it harder to.
Okay.
Yeah, and I already know that this other way of doing it does the job nicely.
Okay.
Yeah. And this one you can check directly that these two are related by mutation with respect to, you know, the green vertices. Yeah, for instance, the fact that here there is an incoming and an outgoing in the composite becomes this one. So this one can be interpreted as arising as the composite of the two arrows on the left. Whereas, you know, here on the original one, you have this arrow, and then you have to add this the composite of these two. So you have to add this arrow, which forms a 2 cycle with this. So in the end, it has to be cancelled. And you see here precisely it's kind of there are no arrows between this side and this side, and somehow that's reminiscent. That's not reminiscent. That's coherent, not coherent. Well, yeah, coherent with. It's in sync with the fact that the 2 cycle here gets removed in the mutation. And for instance, here this arrow has to be reversed. Yeah, okay. So you have this arrow here. So this arrow here can be interpreted as being the reversal, the result of reversing this arrow. And you can kind of one can just keep doing all these little details to be convinced. Or if you want, read the matrix, compare. Okay. Yeah, okay. This is actually a general phenomenon. So this example is actually true. So this is true. True for arbitrary triangulations, but one has to introduce certain type of triangulations. Of surfaces with marked points. Oriented surfaces with marked points. I'm not, at least not for today. At least today, I'm not going to say like about this what I mean by tag triangulations. Let me just say, in the case of an arbitrary surface with marked points, the surface may have boundary, may not, and usually has punctures. If one considers triangulations as we always consider, then there are some degenerate situations. I mean, there are some triangulations that look so degenerate that there are some arcs in there that cannot be flipped. So this one here could be flipped. There are some weird situations for surfaces, for arbitrary surfaces with marked points, where some arcs cannot be flipped. And then in order to be able to flip them, it's kind of you force the machinery and you introduce a new type of triangulation called tag triangulation. So you kind of you enhance the set of what you call triangulation, and within this bigger set of what you call triangulations, the flip is always possible. And then I'm just going to say, so in a surface with marked points, one, the degenerate situation I'm referring to is that one may have these two marked points, and in your triangulation, you may have these arcs, so these loops surrounding this puncture, and this other one. And when you want to flip this, you can't, because you would like to erase it and replace it by another one. But this one, if you erase it, you cannot replace it. So it's not, this one cannot be flipped. Hence, you perform some combinatorial trickery to enhance the set of what you call triangulations. And the new set is the set of tag triangulations. But at least for the moment, I'm not going to say more about this. And I will probably never say anything about it. Okay. But so you see, it's kind of at least here you can see that mutation is the combinatorial recipe that allows you to keep track of what happens to the quiver after flips. So in a way, I think it begins looking like not such a strange combinatorial operation. It's at least combinatorial counterpart of some other move. Okay, now seed mutation. So as I said, what we have seen so far is only the combinatorial datum and how the mutations of the combinatorial datum looks like. So now it's on the more algebraic side. Definition. A seed. Yeah. So before that, sorry. I know that. Before that, let F. F. It's kind of calligraphic F. Be the field of rational functions. In n plus m indeterminates, algebraically independent indeterminates, or variables if you want, with rational coefficients. Okay, then a seed in F consists, is a pair, Q comma, let me say U, it's like mat BBU or mat BFU, I don't know, consisting of and Q is a quiver, you know, with n 1 plus n mutable, 1 to n mutable, and n plus 1 to m frozen vertices. So these are, of course, the vertices of Q. And second, U is an n plus m. Yes, it's an n plus m tuple. Yeah, of algebraically independent. So maybe let's see. In F, lives in F to the n plus m, and it's algebraically independent. Well, I mean, in this case, of course, over Q, right? Over Q. If I had decided to take, I don't know, let's say complex coefficients, then I would say I would just take algebraically independent over C, for instance. Yeah, and some people request that this generate the whole field. I don't care too much. Yeah, so that's a seed. Yeah, and then mutation of seed. So suppose is Q U is a seed. I'm sorry to say one more thing. So Q is a quiver, but I request that I require from the quiver not to have loops and not to have 2 cycles. I mean, so that it actually comes from a skew symmetric matrix. Okay, now suppose that I have a seed, and then the mutation mu k of Q for k in the mutable set is well, let's say is so it's mu. Sorry. I said I wrote mu kq. It should be mu k of q u. Q u. So is, let's say I write it as mu k of q. So that one is already done, and then I'm going to write, I don't know, maybe mu k of u, although that notation is a bit ambiguous, but let's say I don't know, u prime, where u prime underline, where u prime underline, or mu k of u underline is, and then what I said at the beginning is that I'm going to keep all of them except the kth one. So this one is u1, etc., uk minus 1, and then I'm going to replace uk, and it's the only one that I'm going to replace. And here it's the product over the arrows going out of k of uj, yeah, plus the product over the arrows coming out coming into k of uj, yeah, and then this divided by uk. Yeah. So this is what replaces the old uk, and then uk plus 1, yeah, un plus m. Yeah. Yeah. Here, it's going to be for the rest of the lecture is not going to be relevant. But here, I should have told you what acid is. That and here when telling you what acid is, I should have put a bit tilde with excuse-metrizable. And then here I should be putting bit tilde. Yeah, and then here I should have been putting something slightly different, but for the lecture it's irrelevant. Here you see it's for each arrow coming out from k, you put uj as a factor. So if there are many arrows from k to j, you put as many times uj as a factor. So it's not that you put it only once. It's for each arrow you put it. Which, if you think about it, it corresponds to somehow putting uj how many times bij, but let's say absolute value in a way. But and then in the other, yeah, I'm not going to go into that.
So only one of the products contributes every time, right?
No, because for each j, yes.
Yes.
Yeah. Yes, so for each index j, uj appears in at most one of the two monomials. Yes, but of course there could be someone appearing here and someone appearing here, and those someones have to be different. Okay, so let me take this example. I can use this. No, let me put it here. Yeah, and so here, let me write maybe, for the diagonals, let me give them some names. So because the vertices are not 1, 2, 3, 4, no? So maybe let me erase the 1, 2, 3, 4. And so that I can use those indices. So let me say 1, 2, 3, 4, 5, let's say. And then the mutation in direction 5, mu 5, yeah, it replaces the quiver by, well, I already know what quiver it replaces it with. So it's this one. Oops. Yeah, with the corresponding indices. 1, 2, 3, 4, 5. It is not mu k, this is mu 5. Okay, that's the quiver. But now, if I started, let's say, I mean, let me now start, instead of calling them u1, u2, u3, u4, u5, let me call them lambda. I mean, just because. So here I would start with, let's say, lambda underlined, equal lambda 1, lambda 2, lambda 3, lambda 4, lambda 5. So here, my lambda prime, let's say, is, or mu 5 of lambda, is, well, all the first 4 remain the same, and then only lambda 5 changes. And the change is I have to divide by lambda 5, and then on top is arrows outgoing, arrows incoming. Okay, arrows outgoing are 1 and 3. Arrows outgoing is lambda 1, lambda 3. Incoming are lambda 2, lambda 4. This divided by lambda 5, which we knew already, right? I mean, it's yeah. This is precisely these are variables. These are rational functions, right? But somehow the effect of mutation seems to be precisely obtain the expression for the new lambda length for the other diagonal. That's actually what happens. That's always the case for arbitrary surfaces with marked points. But for that I to state it correctly, I would need to say, okay, so over there, work over. Yeah, no, I will leave it for the moment like this. One does need some care. Maybe later I will come back into what subtlety there is in order to be able to state the general theorem. But maybe for the moment I leave it like that. So that's seed mutation. Yeah. By the way, notice here the fact that I'm talking about triangulations of the square. Somehow that context forces me to consider the sides as frozen, because I cannot flip them. And unlike this one, here somehow I don't want to flip them. Like here I want to, but I can't. Here I can't, and I don't want to. So somehow I'm forced. But you see, this means that then if I really think of them as frozen, first of all, the original matrix doesn't see these arrows. And second, these arrows would have to be deleted after mutation. So that's why I don't like the fourth step. But humor me. The point is that it doesn't matter if I draw these arrows or not, and I draw these arrows or not. For the mutation of the rational function, it was completely irrelevant, and that's what I care about. That for these rational functions, considering them or not be relevant, consider the arrow, these arrows connecting frozen or not. Yeah, since it's irrelevant for the mutation of the rational functions, like, okay, I don't care. If you want to draw them, draw them. If you don't want to, don't draw them. Okay, and this statement that I made is general. It's not just this example, it's really in general. Okay, another example. Here you have the so-called Kronecker quiver as your starting point, and now here I have U1, U2. I mutate once. Here everything is just arrow reversal, because here every arrow is either incoming or outgoing for each vertex. So yeah, but then you see mutation at 1, it replaces U1 by, well, you have 2 arrows outgoing, so U2 has to be to the square, because it's for each arrow you put one such factor. Then there are no incoming arrows, so you put a 1, it's the empty product. Then divided by the old one. Mu2, you take now this one, and you replace U2, but U2, you see now again, it's the U1 for this one square. So here square plus 1 divided by U2. And now this one, of course, now you simplify. Yeah, now mu1, and now mu1, and then you have to replace this one with something. So what's the something? It has to be this one square divided by this one. So this one square, yeah, divided by this one here, and then this plus 1 from the fact that here there are no incoming arrows. Yeah, and then here there is something interesting starts happening, which is here when you want to simplify, and then okay, you start simplifying, you keep simplifying, yeah, you keep simplifying, and at some point you notice that some cancellation happens in such a way that the final result is just a polynomial divided by a monomial. So this a priori was, you see, if you show me this, I think I say, okay, this is very likely to survive in the denominator. So a priori, what I could say is this is a rational function. At least I know it's a rational function, but somehow, in general, I would not dare to predict that that precisely that stuff was going to be cancelled. The stuff that somehow prevents this from being a Laurent polynomial gets cancelled. And this is a general phenomenon. Yeah, but I have to define first what the cluster algebra is. So definition. Suppose we are given a seed. So QU is a seed. Yes. It's a seed. Yeah, and then let this calligraphic X. So this is like a madcal X, capital X, be the set of all rational functions that appear in any seed in any seed of the form in all seeds, right? I mean, I consider all possible seeds of the form mu k l, mu k l minus 1, etc., mu k2, mu k1 of q u with the indices k1, etc., to kl mutable. Yeah, by the way, I'm asserting that that mutation of a seed is a seed. So in particular, I'm asserting that that after when I take a seed and I mutate it, that the new tuple is also algebraically independent. But that's a very easy exercise. Of, just take a polynomial expression in the new n tuple equal to 0, and then well, that polynomial, like from there you can form a polynomial expression in the old one by replacing the kth one with this binomial divided by this, and then the algebraic independence of the original one tells you that blah 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 blah, and then the polynomial has to be, all the coefficients have to be 0. So it's not hard. Yep. Another property that I also skipped is we know that mu k of mu k of a matrix is the original matrix. The same is true for seeds. Mu k of a seed is the original seed. And I will say what this implies in a moment. But, okay, then one the elements of this calligraphic X, which looks like a chi, but are called cluster variables. And second, the cluster algebra with frozen coefficients. I mean, with coefficients associated. The cluster algebra, instead of associated, let me just write. This is like MathCal A of QB of QU. Sorry. Is the following, is the u n plus 1, etc., u n plus m subalgebra of subalgebra of f of the original field generated by X. So by all the cluster variables. Notice that here U is really the original tuple is, as we said, un plus 1, etc., un plus m, and these are never mutated. So this means that these one are preserved all along the way, right? So these ones actually belong to X, and since they belong to X, when I say this subalgebra of generated by this, somehow I'm really saying just the subring generated by X, right? So I'm really being silly when I write this, but I wrote it this way because some people don't take that subring. Some people put the Logon polynomial ring here. Yeah, and this is a kind of a matter of taste. Yeah. Okay. Then what else? Ah, yes. So notice this. Since mu k. Yeah. So let me make this observation that let's say that what I have is QU and Q prime U prime related by a mutation mu k. I grad these arrows in both directions because I know that mu k of u is mu k of this one is this one, and this means that if I start with this one and mutating all around, yeah, then the rational functions I obtain are precisely the same as if I start with this one and I start mutating around. So in other words, if I consider any seed of this form that can be obtained from the original one by a finite sequence of mutations, then the cluster algebra associated to this one is exactly, again, this one, as sets. They coincide. Yeah, so that's a consequence that one can easily draw just from also the simple fact. I mean, the fact is simple to prove that mu k of mu k is the identity. Okay. Then examples. Yeah, that's where I have to say about this one. So let me think. Let me leave it there.